A few days ago I posted a video that seems to have caused a bit of controversy, and it was in relation to an observation or a comment that was made on that video, and I posted a follow-up video, and I'm now going to refer to the incident as Fusegate. Some of the younger viewers might not get the humour there, but I'm going to stick with that anyway. And it is one of the things in electronics that I find fascinating, and it is one of the reasons I enjoy electronics so much, is because I learn something new every day. And sometimes just the simple things are quite interesting, and things that I learned years ago, it's clear that maybe not everyone is aware of them. Those of you that are, hopefully you'll share in the interest, and those that aren't, hopefully you'll find it interesting as well. And in this case we're going to look at a simple piece of copper wire, and its behaviour is not quite as straightforward as you might first assume, and that's something that came out of the comments in relation to this fuse incident. And the comment related to partway through one of the sequences in the video, the fuse seemed to start glowing for no apparent reason. And I think the viewer put it down to the fact that I turned the supply off and had turned it back on again for that segment of the video, but I hadn't. It had been running for several hours, and I thought I'd demonstrate something in this video just by way of interest. It's one of those things that I find interesting, and hopefully you'll find it interesting and or informative as well. So before I start, I'll just show you the setup I have here. Now, one thing you need to be aware of, and I'm sure any YouTuber will say the same thing, is that there's far more going on outside of the field of view in the video than you might be aware of. And especially for someone like me, that I do hundreds or thousands of repairs every year, some big, some small. I do restorations. So if I say in the video I'm going to leave something running for an hour, it's very rare that I will go away and sit down for an hour. I'll go and work on something else for an hour and then come back to it. So I've had comments that there are noises, buzzes, hums. Well, there's a lot going on in this room from the electronic perspective, so unfortunately that's just the way it is. There are other things, and I don't have expensive camera equipment, so it does tend to pick up noise, especially the microphone. So one of the things that I have in this room, because it is in my house, is a set of extractors that sit just above this bench, and there's multiple outlets. I can turn them all on, blow or suck or whatever. That's also the reason, incidentally, why you may see in some videos when I use the thermal camera the room seems fairly cold, and that's because it draws air in from outside and blows it back outside through the extraction system. It does tend to keep the room fairly cold. There is a heat exchanger on the outlet, but even so, I lose a lot of heat that way, and to prevent the entire house getting too cold, the room is kept isolated, but it does tend to get fairly cold in here. In fact, if I turn the thermal camera on now and we have a look, the extractor is not running at the moment, but it has been all morning, and if we look, we'll see that the current temperature is under 17 degrees, and that's one of the side effects of the extractors running all the time. So just to show you the setup I have here before we begin, it's very similar to what I had when I was testing the supply in question. If I just raise the camera just above the field of view, and that's the extractor in question, or at least the end of it. There are a number of those across the bench, and I'll just position them when I want them so that they're above where I expect any magic smoke to be released. So I'll just put the camera back down. Okay, so what we're going to be looking at here is what happens when we pass a current through a piece of wire. And so what we have is one of the Ryden bench supplies, a multimeter, and all we're doing here is we're taking the output from the supply. The multimeter is connected across the output to give us a more precise indication of the voltage coming out of the supply. And all I'm going to do is take one of these, so I've got fairly thin copper wires coming out of it, and they are copper, and we'll connect that directly across the power supply. Now, I'm not connecting the resistor across the supply, I'm connecting the supply just across one of the lead ends, so the resistor's not in circuit, it's just a piece of wire. And what we'll do now is turn on the supply. It's set to a voltage limit of 2 volts and a current limit of 1 amp. And I don't know how clearly you're going to be able to see the wire down here, so what I'm going to do is turn the lights down in here, so hopefully you can see the wire a bit more clearly. Now at the moment the extractor, which is sitting, it's just up there, that's the end of the black tube I showed, is off, so there's no air moving, but there are other things going on in the lab, so we may see certain effects that are not directly related, and again that's part of the point. Now at the moment, if we point the camera at the wire, you can't really see much. It's probably getting slightly warm, but not warm enough to show up. I'll try increasing the current, so we'll go up to 3 amps. So still nothing really showing on the thermal camera. We'll go up to 4 amps. Okay, now we can start to see the wire beginning to glow on the thermal camera. There's nothing visible in the visible range, it's just on the thermal camera. We'll go up to 4.5 amps. And we're now beginning to see it glow a bit more clearly on the thermal camera. Still nothing in the visible range. What we'll do now is get the thermal camera out of the way, and we'll watch this directly. As I say, I'm not quite sure how clearly this will come across, so I'm going to dim the lights so you can see more clearly what's going on. Okay, so we're at 4.5 amps, but if we watch the multimeter voltage, you'll notice it is fairly stable at around 0.306 volts. What I'm going to do now is start increasing the current slightly. Now the supply that I was testing was drawing just around 5 amps going through the fuse, so we'll work our way up to that. So we'll get up to 4.7 amps. Of course we're getting an increase in the voltage across the piece of wire because the current flowing through it is a lot higher. But again, notice the voltage is relatively stable. We'll have a quick look at the wire through the thermal camera. Now it's got a bit more current flowing through it, and you can see it is now starting to glow quite significantly on the thermal camera. But if we now look at the multimeter, we can see the voltage is slowly creeping up to a slightly higher value, then it will stabilize. One of the questions I got from somebody else about the video was that it seemed to take a long time, and I hadn't even noticed it in the video at all until it was pointed out, and it had been about 10 minutes since I turned the extractor off, so it did seem quite slow to heat up. But this is what I'm trying to demonstrate in this video. We can see the voltage is still rising. I haven't made any other adjustments, and of course what's happening here is as the wire heats up, being copper, its resistance increases, and so the amount of power it's dissipating also increases because the current is fixed. We're putting a constant current through it, so as its resistance goes up, the voltage across it rises, and hence the power dissipation in the wire increases. That makes it get even hotter, and so it dissipates yet more power, and so this kind of runs away. You get to a certain point where the wire will go from a dull glow to just blowing open in a few seconds, and we'll try and demonstrate that. It's quite difficult to demonstrate because, as I said, it's fairly quick. It's a bit more unpredictable on the actual supply I was using because the wire was soldered to some fairly big thermal masses, some fairly big soldered junctions at each end, which tend to conduct a lot of heat away, so it's a lot more unpredictable like this. So we'll start increasing the current again. So we'll go up to 4.8 amps, and of course we get an immediate rise in the voltage, but now if we watch the voltage it will continue to creep up. We'll get the thermal camera back in and see what's going on. We still can't see any visible glow from the wire yet, but I'm sure we can see something on the thermal camera, and sure enough we can see that starting to heat up. The voltage on the multimeter is still rising. Now one thing I'm going to do here is, this is one of the things I was trying to explain in my response to the comment in the video, is that there are many things that affect this. It's not just a case of it's always going to glow at a certain rate, and this is one of the reasons that fuses really need to be enclosed. If we watch this value on the multimeter, I'm going to turn the extractor on. And so I'm not adjusting anything else, and this is just the effect of the extractor. And there is not a huge airflow on here, and although I said in the video there was no airflow across the heatsink, I was talking about the forced air that's normally blown across here. This is just a very gentle airflow. There's hardly anything moving down in the bench area. This is just extracting to try and remove any fumes should something go wrong. So we can see that the voltage has dropped quite significantly, so I'll turn the extractor back off, and if we now watch that voltage, we'll see it rising again as the wire heats back up. To help things along, we'll increase the current and we'll go up to 4.9 amps. So now 4.9 amps. Still no sign of the wire discoloring or starting to glow. It will be getting quite hot, and we'll have another quick look through the thermal camera, and we can see it is now starting to get significantly hotter than it was when we started. The voltage is continuing to rise, and so what we'll do now is we'll go up to 5 amps. And this is about the current that was being drawn by the power supply, so this is now very similar to what was going on within the supply. Now notice that the wire is not yet glowing. I'll just briefly turn the light off, so there's nothing visible in the visible spectrum from the wire. It will be getting very hot if we look through the thermal camera, but we can see that the voltage is starting to rise now quite steeply, but the wire is now, as you can see, getting quite hot. But it is taking a long time to heat up. Now if we go up a little bit further, so we'll go up another 50 milliamps, which you wouldn't think would make that much difference, but notice now that the voltage across the wire is starting to rise quite quickly. I'm not adjusting anything else. The voltage and the current from the supply is staying the same. Actually the voltage is rising, of course, in response to the increase in resistance. But we can see that the voltage across the wire is rising. It's not helping the fact that I'm talking all the time, because I'm kind of blowing across the wire as well, so I'll just keep quiet for a few seconds and we'll watch what the voltage does across the wire. And you can see when I stop talking it starts going up. I'll turn the extractor back on for a few seconds and watch the voltage across the wire. So I'll turn the extractor back off, but as you can see, although there's very little airflow, it is quite significant because of this kind of compound effect of the temperature increasing the resistance, which increases the voltage across it, which increases the power dissipation. So once you get onto that what is almost an exponential curve, then very small differences in airflow can make a big difference. And if we now keep going up in currents, I'll go up to 5.1 amps, we can see the voltage is now starting to rise very quickly. I'll turn the light off and we'll see the wire starting to glow very soon. You probably can't see it, but the voltage according to the multimeter is now just on 0.41 volts. It's still rising very slowly. It's still rising. I'm not adjusting anything else. This is just time. We're just sitting and waiting. Okay, so it's reached what seems to be a plateau at 0.413 volts. So we'll go up another 10 milliamps. So you'd think that we're at over 5 amps here, so at 10 milliamps isn't going to make that much difference, but the voltage has started to rise again and it's continuing to rise. So all we've done is gone up by 10 milliamps here. We're now at 0.42 volts. It's still rising. So a very small increase in current in terms of a percentage has raised the voltage across the wire quite significantly. We'll go up another 10 milliamps. Another 10 milliamps. Another 10, so we'll go up to 5.15 amps. Go up a bit further, so 5.17 amps. So this is about the level of current that the power supply was drawing. And although there's nothing visible on the wire yet, it will probably start glowing very soon. So currently we're at 0.458, 0.46. So the voltage is increasing quite quickly now. 0.466, 0.468. Still rising. So although we're not increasing the current, the voltage is continuing to rise. I'm doing this in real time, by the way, to make sure there's no chance that what I'm showing could be taken out of context or there's any scope for confusion here. So excuse this for going on a bit longer than it really needs to, but I won't edit this out. I'll show everything. So we're now at 0.5 volts and the voltage is now starting to rise quite rapidly, 0.51, 0.52. When the wire starts to glow, I'll try and maintain about 0.6 volts to stop it just blowing open circuit. So we're getting to that point now. It's starting to glow. I'm now turning the current down. Hopefully you can see the wire glowing, and it blew open circuit. So even though I reduced the current quite significantly, let's turn the light back on, the wire blew open circuit and it still failed at a much lower current than the peak current. So I'll replace the piece of wire, we'll do it again, and this time I'll turn the extractor on when the wire starts to glow, and we'll see the effect that that has. So I'll just replace our piece of wire. Okay. You can see the voltage rising quite quickly. I'll turn the light back on so you can see the multimeter, because it's probably more informative than seeing the wire glowing, and hopefully you can see the wire glow anyway. Okay, so in order to stabilize the wire is now glowing. I don't know if you can see it, the wire just glowing gently, but to stop the wire from blowing out, I've had to reduce the current by about half an amp. So the current has gone down quite significantly, but it's still glowing red. What I'll do now is I'll turn the light out and I'll turn the extractor on. So you can hopefully see that glowing. I'll turn the extractor on. And the glow is immediately gone, and the voltage across the wire has significantly dropped. I'll turn the extractor off and we'll see the wire heat back up fairly quickly. Although it still takes quite a long time, because it's trying to get up to the point where the resistance is rising, and once it reaches that critical level, then it starts to heat up much more quickly, but it does take quite a long time. You can see it's rising, but very slowly at this point, and it'll start to accelerate as the wire heats up. So I'm going to increase the current again, so we'll get to the point where it's likely to fail if we leave it. And once it starts to glow, I will turn the extractor back on. So we're getting to that point now. The wire is now starting to glow. I'll turn the extractor on, and if we watch the voltage on the multimeter, so though there's very little airflow, in fact almost no airflow across this at all, it's still having a significant impact on the temperature of this. As I say, it's why fuses need to be enclosed to be accurate. But as you can see, hopefully this helps to answer what was being seen in the video, and it's also a very interesting thing to experiment with and watch. You wouldn't think something as simple as a power supply, a multimeter and a piece of wire could be interesting, but this is the sort of thing that can be quite fascinating. What we'll do now is we'll see how far we can take this. Like I said, there's very little airflow, and you've seen that me just talking will tend to reduce this anyway. I'm going to leave the extractor on and start to increase the current and see what happens. Before I do that, I'm just going to increase the current up to 5.1 amps. And we can see that the voltage across the wire has stabilized. I'll briefly turn the extractor off, and if we watch the voltage on the multimeter, you can see it's very rapidly rising, and it's increasing in the rate at which it's going up. I'll turn the extractor back on again, otherwise the wire will blow. And you can see immediately the voltage starts to drop again. The reason I turn the extractor off, I don't know how loud this comes across on the video, but it is quite an annoying noise to have going continuously on the video, which is why I turn it off. But if it's not annoying you, then let me know and I'll leave it on in future, but I think for the sake of the videos it seems to be better with it off. So what I'm going to do now is increase the current until we get to the point where it's likely to fail, and then we'll turn the extractor off and see what happens. So we're now well above the current that it would survive previously. Now of course here we're getting kind of the opposite effect, where it's struggling to generate heat because of the airflow. Even though it's a very low airflow, it's sufficient to keep the fuse wire cold. So we're now up to 5.3 amps. We'll go up a bit further. We'll go up to 5.4. No sign of the wire glowing. It starts glowing at about 0.6 volts, so we're not at that point yet. We'll go up to 5.5 amps. And we are now getting to the point where the wire is likely to fail. So I'm going to go down a little bit, just enough to get the voltage to start to drop again, and then we'll try and stabilize it. So it's about there, it's about 5.44 amps. What I'm going to do now is turn the extractor off. If we keep an eye on the wire down here, we'll see that it will not last more than a few seconds. So I'm going to turn the extractor off now. And we can see that the wire is heating up very quickly and then it fails. So I hopefully found that of some interest. As I say, it's quite fascinating with electronics how sometimes some very simple principles can all conspire to create something that on the face of it seems to be creating a bit of an anomalous result, but it is the nature of electronics that this is the sort of thing you have to watch out for when you design equipment, and you do need to cater for this sort of thing. Cater for resistance, changes in leads when you design something. I think we mentioned this when we were designing the ride and power supply. So it's always well worth considering these sorts of things. If you're designing transformers, remember you'll get a significant resistance change in the windings as the transformer heats up. And this is the sort of thing that you can see, and it doesn't take a great deal to push it over a limit one way or the other. So I hope that was of some interest. As ever, comments are welcome, and if you do have any queries about something you see in one of my videos, then please let me know. Okay, I was about to post this video, but realised that I hadn't mentioned something that was probably relevant, and someone's bound to point it out if I don't mention it, and that is that fuses are not normally made from copper wire, and it's specifically because of the behaviour I've just demonstrated that copper wire is not used in fuses. I use copper wire for this type of testing simply because, as you've seen, you can set a very fine threshold where if the current being drawn starts to rise even slightly, you'll get a runaway effect and the fuse will open. In this case, the copper wire will open, and that's what I want for this soak testing. I don't want to wait for a big overcurrent event. What I'm looking for is if something starts to fail within the circuit and the current starts to rise, I want the fuse to open, and that's not the sort of behaviour you get with a normal fuse. So by way of demonstration, what I've done is I've replaced the copper wire with an actual piece of fuse wire. It's made from a different sort of metal, and we'll see that its behaviour is different to the copper wire. So it's a 1.5 amp fuse wire. I've currently got 0.8 amps going through it, and has been for a while, so it's stabilised. If I now turn the extractor on, the extractor's in the same place it was before, you can see that the effect is still there, but it's nothing like as dramatic as it was. It's only about 20% of the change that we saw with the copper wire. I'll turn the extractor back off and we'll continue to increase the current going through this fuse wire. If you remember with the copper, we got this sudden runaway effect. So we're now getting quite close to the fusible limit, and in fact the wire is starting to smoke. You probably can't see it on the camera. I'll get the thermal camera, see if we can see anything on that. So as you can see, the fuse wire is very hot. But it's not running away like the copper wire did. I'll turn the extractor back on. We've currently got 1.2 volts across this. So again, you can see it drops, but not by the dramatic amount we saw with the copper wire. But more importantly, it's not running away and suddenly opening. We'll keep going up in current and we'll see the behaviour of the fuse wire very different to the copper. So it is now glowing red. I'll turn the lights off so you can see it a bit better. But if you remember with the copper wire, it started glowing and then very quickly went from a dull glow and went straight through and went to open circuit because the resistance increased so rapidly. But with the proper fuse wire, we're getting quite a stable response, and in fact the voltage across it has now dropped. If I turn the extractor back on, you can see the effect is very small compared to the copper wire. So we'll keep going up. So that's now the rated limit for this piece of fuse wire. And although it's still glowing, I'll turn the light back out. It's kind of stable, it's not suddenly starting to glow and then running away. So we'll keep going up to 1.6 amps, glowing quite brightly now. 1.7. So as you can see, although the voltage is rising, that's rising in relation to the current flowing through it rather than just the fact it's getting hot and the resistance is increasing. I'll turn the extractor back on. So again, there is an effect, but nothing like what we saw with the copper, and I'll keep going now till the fuse fails. So it's glowing quite brightly, but it kind of stabilizes. It glows brightly, but it doesn't kind of run away and suddenly open. So very different behavior compared to the copper wire. And finally it opens at 1.9 amps. So very different behavior, but that's why I don't use fuses to protect when I'm doing soak tests on vintage pieces of equipment. There is a fuse in there, of course, if something goes wrong, but by using copper I can set a threshold where even a slow change and maybe 10% increase in current will tend to make it go open circuit, and that's what I'm looking for in certain types of testing, which is why I use a piece of copper wire in that specific test. So I hope that helps to clarify things a little bit. Any comments are welcome. And as I said, I don't normally go into explanations like this in videos because otherwise the videos would go on forever. If I went down every technical rabbit hole that comes along to explain every anomaly that we see in the videos, then the videos would go on forever. But if there's something specific you want me to explain, that's fine, but I'll do it in a separate video. I won't make the videos ridiculously long by trying to explain every little thing that crops up in them. As much as I can, I stick to the topic of the video. The topic of that video was not the fuse, it was the power supply, but I hope you found this particular video interesting. As I said, there's always something interesting to learn with electronics.